the previous lecture in this series, I reviewed classical field theory, but I decided to skip over deriving the Euler Lagrange equations, as I said that I have done that in one of my videos in relativity series. But I think that I thought about it, and I think that it's not a good idea, right? So now for this video, I decided to start with the derivation of the Euler Lagrange equations and then the equation of motion. And then we would extend that towards the symmetries in classical field theory, where we will talk about Noether's theorem, and we will see the beauty of Noether's theorem. So before I even start, I would like to point this out that we tend to use Lagrangians instead of Hamiltonian in quantum field theory that are this thing. And that is simply because of the fact that Lagrangians are Lorentz invariant, right? And we know that that is a very important deal for us, right? Now, the dynamics for a Lagrangian system, a system which is defined by a Lagrangian, is determined by what is called the principle of least action. And the principle of least action is defined as S, which is your action, is the time integral of your Lagrangian. But now if you move towards the 4-vector formalism, then you can write this down as the integral d4x of your Lagrangian density, right? Okay, now this Lagrangian density is a function of your field and the derivative of the field. So you could make an analogy with a position and velocity, right? So this could be thought of at least as position, and this is the velocity, right? Okay. Now, what we are going to do is we will start with varying the field as phi goes to phi plus delta phi. And the reason for this variation is that this variation is simply going to, it is an infinitesimal continuous transformation of the field, and it produces what is called the infinitesimal symmetry in our equations of motion, which we will derive, right? Okay, so that's the reason that we are going to make this sort of variation. Now let's start with an example, right? Let's not start with an example. Let's just write down what is delta S, right? But also know that from principle of least action, we have that delta S is 0. It vanishes, right? So the change in action is 0. That is your principle of least action. So if we have to write down delta S, that is the change in action, we know that it is the integral of your Lagrangian. So we have to consider what is the change in your Lagrangian density. So we can write down delta S is equal to the integral d4x times, now let's look at the derivatives of this Lagrangian density, the change in this Lagrangian density, that would simply be partial L over partial phi times delta phi, that is the change in your field, plus partial L over partial times partial mu phi times the change in the velocity of the field. So that would be partial mu phi, right? Okay, now I wrote this equation down by noting the fact that this is how my action is defined, and the fact that this is my Lagrangian density. So it's a function of the field and the derivative of the field. Right, okay, now if you carefully look at this equation, right, this one, let's look at this second term over here. What we can do for this is we will start with applying what is called the integration by parts, right, from your boring calculus. Okay, so how are we going to do that is we will take the derivative of this term, that is partial over partial x mu of this term. So well, not exactly this term, but it's partial L over partial mu phi times delta phi, right? So we are taking the derivative of this term. We are just taking this partial mu outside, right? Because it is the partial derivative, and we already know that partial derivatives commute with each other. Also, note that partial derivatives not only commute with each other, but they commute with variations as well. So they will commute with this delta phi, right? Okay. Right, so from here now, let's solve this thing. What would this be? Well, we apply the derivative to first term and to the second term. So we are going to use what is called the product rule of derivatives. So what would that be? Well, for the first term, that's partial over partial x mu on partial L over partial times partial mu phi times delta phi as it is, and then partial L over partial times partial mu phi as it is times now note that I said that partial derivatives commute with variations, so I can take this delta like this, and I can say partial phi over partial x mu. So that is what this thing is equal to, right? Okay, now if you carefully look at this, this term over here, that is this one, is the same as this term over here, right? So what we can do is we will subtract this term from this term, right? So to get this term, right? So let's do that. What's that? Well, it's simply partial over partial x mu partial L over partial mu phi times delta phi minus partial over partial x mu partial L over partial mu phi times delta phi, right? And what is this equal to? Well, this is equal to this term over here, so that's partial L over partial mu phi delta or let's say that the derivatives and deltas commute, so let's just write it partial delta phi over partial x mu, right? Okay, so right, well, if you did not understood why these terms are equal, well, if you look at it, everything is the same except for, you might say that this partial over partial x mu, where is that? Well, that's just this thing. So partial mu is just partial over partial x mu, right? Okay, so yeah, let's get rid of this. Now the next step, or the next, well, logical step, is simply to replace this term that is over here with what we have over here, right? Okay, So let's go ahead and do that in this equation. Let's replace it. So let's see what do we get. Well, let's write it down. Delta S would be equal to the integral d4x, and well, this first term as it is, which was partial L over partial phi delta phi, and then let's replace it. When we replace the second term with this one, what do we get? Well, we get partial over partial x mu partial L over partial mu phi delta phi minus partial over partial x mu partial L over partial mu phi and delta phi, right? Okay, now what we will do is I will simply make some arrangements in this equation, and those are as follows. Well, we have this thing as it is. Let's consider this term, this one, or let me actually highlight it. Let's consider this term, right? And let's also consider, well, this one. So doing so, what we see in both of these terms, we have delta phi, right? Okay, so what I can do now is I can factor delta phi outside. That is just, I can throw it out. So what do I have? Partial L over partial phi minus partial over partial x mu of partial L over partial mu phi, right? This thing, and these delta phi, I'll throw them outside. So that's like this. We have this thing, and then we also do not forget that we have this term. So let's write it down separately. That's plus the integral d4x partial over partial x mu partial L over partial times partial mu phi delta phi. Right. Now the interesting thing is that this integral, let me highlight it, this one is simply the integral of your total derivative, right? This thing. And from calculus, we know that it just means that it is the integrand which is evaluated at the boundaries of the field. So, but actually the fun and the exciting part is that this delta phi, this thing, it vanishes on the boundaries, right? Because outside the boundaries, we do not have any field. So it would vanish at your boundaries, right? Okay, so, well, that's one thing, but we also know from principle of least action that delta S also has to vanish, right? So, well, boom, we can use these things, and we can simplify this horrifying expression that is over here. So in fact, this one, right, this expression, it looks pretty lengthy, but what comes out from this expression now is that we can say that the above, this integral that we have, this one, well, I forgot to mention, I think this integral will be 0, right? And why is that again? Well, that is simply because this integral, that is, I set this equal to 0, it is evaluated at the boundaries, but we know at the boundaries that delta phi is 0. So once I replace this one in this would just vanish. It would give me 0. Right. So we are just left with this integral then, this one. And this integral can only vanish if the integrand itself vanishes. So what is inside the integral, right? That has to vanish. And from this then, what we have is, then that integrand is partial L over partial phi minus partial mu partial L over partial mu phi is equal to 0. It has to vanish. And voila, this is what is known as your famous Euler Lagrange equation, right? What we can do over here is, well, we can even we can open this thing, right, and write it as partial L over partial phi minus partial over partial x mu of partial L over partial mu phi is equal to 0. So these two are just the same things, right? They are equal. It's just that I have expanded this partial mu. So sometimes you might see the equation like this, and sometimes you might see it like this. Just pointing this out so you don't get confused. Hopefully you would not, right? But what do these equations tell you? Well, these are the equation, or this is the equation that will give you the equations of motion for a particular Lagrangian, right? So they provide you with the equation of motion. So with this then, we have successfully derived what is called the Euler Lagrange equation of motion, right? Or Euler Lagrange equations. And from these then we can find out what would be the Euler Lagrange equation of motion. Right, so now we can move on to the symmetries in classical field theory. And to talk about these symmetries, we have to, or we actually have this one very beautiful theorem, which is known as your Noether's theorem. Now, before I move on to giving you what the statement is of the Noether's theorem, let's actually arrive at that statement first. So what may happen is that your Lagrangian that you have for a system, it may be invariant under some special type of variation. And that variation I already mentioned at the start of this video could be phi goes to phi plus delta phi. So consider that in this variation, the Lagrangian remains invariant. So let's start off with an example, and this time let's consider what is the complex scalar field. So the Lagrangian for the complex scalar field is given as partial mu phi squared mod squared minus m mod phi squared, right? Now, if you take a look at this Lagrangian, your task is to first figure out that under what field transformation is this Lagrangian an invariant. So if you look at it, you quickly realize that the Lagrangian is invariant under the U1 group transformations. And what is that? Well, that is simply if I were to take my phi and transform it as exponential negative iota alpha, where alpha is just, it belongs to your real field, times phi, right? So for all alpha that belongs to the reals. Now I said that it is this thing comes under U1 transformations, and you can check that if I were to take this unitary dagger u, which would be exponential iota alpha times exponential negative iota alpha, and this thing is exponential 0, which is unit, right? Okay, so that means that if I make this sort of a transformation, nothing will happen to the Lagrangian, right? Okay, and you could do that as an exercise yourself. Take this field, this one, and substitute it in this Lagrangian, and you will see that you would get back the same Lagrangian that we have over here. Right, now this transformation then of the field is known as a symmetry of a Lagrangian if it leaves your Lagrangian invariant. Now note that we're talking about complex field, so let's quickly look at how do you write down a complex number. Well, we say that z is equal to u plus iota v, right? So what that means is then a complex field has two real degrees of freedom that are independent of each other. So one is from this one and the other one is from this one. So with this then I can write down my complex field as phi is phi 1 plus iota phi 2. Or I can even write this down in a much more neater notation. I could just say that I have these two independent fields that are phi and phi star, right? So with this then I can take this Lagrangian, right, this one, and I can write it down as follows. So that's Lagrangian density is partial mu phi star minus m squared phi star, right? Now this from this you can see that the symmetry transformations that we defined earlier over here for our field, there would be two of those. So one would be for the field phi, right, and that is simply that it transforms as exponential negative iota alpha phi, and the other one would be for its corresponding conjugate, a field that is phi star transforms as exponential iota alpha phi star, right? Now from here, what you can do is you can derive the equation of motion for this Lagrangian. And let's actually go ahead and do that. It would be an exercise for us for what we learned earlier in this video for our Euler Lagrange equations. So if you recall, what was your Euler Lagrange equation? It was partial L over partial phi minus partial mu partial L over partial times partial mu phi, which is equal to 0. But you have to note over here that we are now considering a complex field, right? And we have a Lagrangian for the complex field. And for a complex field, we have two independent degrees of freedom. That simply means that you would not have one Euler Lagrange equation of motion, but instead you would have two Euler Lagrange equation of motion. So what would be the other one? Well, it is obvious that it would be partial L over partial phi star minus partial mu partial L over partial times partial mu phi star, which is equal to 0. Now first let's consider this first Euler Lagrange equation of motion, and let's solve for this one using the Lagrangian density that is given over here. So let's go ahead and do it, right? So we can simplify or we can expand this Lagrangian density as phi dot star phi dot minus, well, why can I do this, right? If you might be confused, I can do that because I have partial derivatives of my field, and these are the four partial derivatives, as in you have four component derivative over here, where the zeroth component is the time or temporal component, and the other two are simply your spatial components. Now, if I take from this my time component as positive, as I have done over here, I have to take the spatial components negative, right? So that's the metric that I'm using. So then I would have negative spatial components derivatives can be written as the gradient, 3 gradient of phi star dot the 3 gradient of the field phi. And then of course we have minus m squared phi star phi. So now this is the Lagrangian that we have. And with this, we can simply first compute for this first Euler Lagrange equation. Let's compute this thing. So what's that? Partial L over partial phi. What is that? If you look at this Lagrangian, we have two independent fields or degrees of freedom. One is phi and the other one is phi star. So if I'm taking the derivative with respect to phi, the other field is treated just as a constant. So well, I'm taking the derivative with respect to phi, and I have derivatives in these first two terms, so those would be just 0. But in this term, we have phi star and phi. So if I take the derivative with respect to phi, phi would go vanish, it would become 1, and we would be left with minus m squared phi star. So minus m squared phi star. So it's just like your elementary differentiation, right? Okay, now the next step is to compute partial L over partial times partial mu phi. And what is that? If you look at this Lagrangian, we have that would, well, it would be simply equal to what is your it would be equal to eta mu nu, and eta mu nu, we're just adding this so we can shift the indices upwards and downwards, so we can remain inconsistent with contracting the two derivatives, right? So we would have partial mu partial nu phi star plus partial nu partial mu phi star, right? And I have just applied the product rule sort of thing over here, and this is then we have both of these things, right? So we just plug them back into the Euler Lagrange equation, and we get minus m squared phi star. If you look back at your Euler Lagrange equation, we are just putting these values over here that we have just computed, right? So minus m squared phi star, and because of this negative sign right over here, that negative sign, we have negative eta mu nu partial nu phi star plus partial mu phi star, and this is equal to 0. Before I move further, I would like to point out that I hope you have noticed that we used this Euler Lagrange equation where we had no, the field was not a conjugate field. And by using this one, we get the equation of motion for the conjugate field, right? And I would like for you to do the as an exercise for this Euler Lagrange equation and derive the equation of motion yourself, and you would see that for using the conjugate Euler Lagrange equation, you would get equation of motion that is not the conjugate, right? Okay, so from this now, this thing is simply the same as partial mu plus m squared right? So in fact, actually I wrote plus over here, this would be negative, right? And so we can just cancel all these negatives, right? Because we have on the right hand side, it's just 0. So this is what we are left with. And we can factor phi star outside. We can throw it outside. So if we have phi star is equal to 0. And this is the differential equation, or the equation of motion that you have for from one of the Euler Lagrange equations. And you can simplify this if you recall that your D'Alembert operator is defined as partial mu. And if I use this in this equation, I get this equation that is the box, or the D'Alembert operator, plus m squared phi star is equal to 0. Now, this equation is what is called your Klein-Gordon equation. And you would have another one, and like I said, that it is your job to derive that using this Euler Lagrange equation, right? And you would see that what you would get is D'Alembert plus m squared times phi is equal to 0, right? So these are the two equations of motion that you have for your two independent fields. Okay, so when there is such a symmetry in your Lagrangian that depends on some parameter, that is alpha, say, let's call it alpha, that can be taken very small. Now what I'm saying is that this just means that the symmetry has to be continuous. Now let me write this down, that note that your Lagrangian density is a function of phi and partial mu phi. But say you have more than one fields, so let's generalize this a bit. So let's add the subscript n to your fields. Now, because I said that the symmetry will be continuous, right? So from that we have delta L over delta alpha has to be 0. It has to be small, so it's 0. Using this, we can derive a very similar equation in the very similar manner as we did for deriving the Euler Lagrange equation. And the equation over here would be that this delta L over delta alpha, which is equal to 0, is equal to, if we write down this expression, we have, well, remember that we have more than one field, so we will sum over n, and we have partial L over partial phi n times minus partial mu partial L over partial times partial mu phi n, and we would have delta phi n over delta alpha. And then we have another term as well, which is plus partial mu times partial L over partial times partial mu phi n times delta phi n over delta alpha. Right, and so this is all I have done is written down the change in Lagrangian with respect to change in the continuous parameter that I defined as alpha, right? Because this symmetry, it depends on this parameter alpha, and if it is very small, then we have a continuous symmetry. Now in this equation, if you look at this thing, this is what? This is simply your Euler Lagrange equation that we have derived earlier. So if this Euler Lagrange equation is satisfied, what that means is, if it is satisfied, then this thing is equal to 0, right? If you remember, we derived it over here, this one, and it's equal to 0, that means the Euler Lagrange equation is satisfied. Then we have this thing vanishes, right? And we are only left with this term that is over here. So, but we also know that all of this thing is equal to 0. How can a derivative of something be equal to 0 is only if this something in this total derivative is equal to a constant, right? That is again from your elementary calculus. So this thing over here, if this thing is a constant, then this above equation, that is this one, is satisfied, right? Okay, so what I can write down over here is then that this partial mu of this thing, which is this thing, which is a constant, so constant is equal to 0. And this just implies the conservation. So what I can do now is, let's just, instead of calling it a constant, let's call it some j mu. And this j mu would be our conserved current then. So this thing is equal to 0. Now what is j mu? J mu is this thing that is written over here. So let's write that down. What is j mu? From this is, j mu is defined as summation n partial L over partial mu phi n times delta phi n over delta alpha. This thing is known as Noether's current. Right. Okay, so now we are almost completely ready to state the statement of Noether's theorem. But before I do that, let me quickly show you a very a short example, right? So let's consider this Lagrangian, which is for the complex scalar field, that is partial mu phi star partial mu phi minus m phi star. And we know that we can write this down as partial mu phi mod squared minus m phi mod squared. Now we know that for this we have the transformation that phi transforms as ei alpha phi, right? This is the symmetry transformation that leaves the above Lagrangian invariant, right? It leaves the Lagrangian invariant, and this transformation is from the U1 group, so unitary group, right? Okay, so with this then I can write down the change or delta phi with respect to alpha, right? Is what? It is simply negative iota alpha phi. And I could also have the other field, that is phi star, that transforms as exponential plus iota alpha phi star. So let's see what is the change in this phi star with respect to this parameter alpha. Well, it's simply plus iota alpha phi star. Now if you look over here, what is your Noether's current? All you have to do is substitute these values in Noether's current, but note that we have summation n, right? So for this complex Lagrangian, we have two fields, and so in this Noether's current we would have two terms, right? One for your field phi and the other one for the conjugate field phi star. Right, so let's write this down. The Noether's current in this case, J mu, would be equal to partial L over partial mu phi times delta phi over delta alpha, and the other term would be for the conjugate field, that is partial L over partial mu phi star times delta phi star over delta alpha. Right, now all I have to do is I have these two quantities, right? Let's just substitute these in this equation. So let's do it. We have j mu. Once we do that, we would have j mu. We see that we have iota like this, or actually let me just write it down completely, right? Let's not miss any steps. So we would have minus partial mu phi star, right? This is this quantity, and we would have iota phi, right? Iota phi from this thing, and then I have plus, I made a mistake over here, right? I made a mistake and I'm sorry, I apologize for that. In these two, when I took these derivatives, it was with respect to alpha. And so I would not have this alpha over here, right? So I hope that you forgive me for this mistake. I hope when I was doing it, you already realized that I was making a mistake. Okay, so this are your quantities, right? So that's why we don't have any alpha in this one. And then I have, let me see, we have this term. This term is simply plus partial mu phi, and we have this thing multiplied by this thing, which is plus, well, we have this plus over here, it's plus iota phi star, right? And we can well simplify this a bit. We can factor some terms out. So we would have j mu is equal to, we can factor iota outside, and we can factor negative sign outside. So let's have this thing, phi partial mu phi star minus phi star partial mu phi, right? So this thing is then the Noether's current for your complex scalar field, right? Okay, now the next step is that we say that this is the conserved current, right? But let's go ahead and prove that it is indeed a conserved current. And how would we do that? Well, we know that if we have partial mu of this j mu, and if that thing vanishes, then that is j mu is a conserved current, right? So let's calculate this thing using this j mu. So what will we have? Well, let's write it down. Partial mu j mu is equal to negative, look at this thing, right? This is your j mu, and partial derivatives commute with each other. So we will have negative iota phi, and we can move these partial derivatives inside. So we would have partial mu, right? Because that's how these derivatives contract with each other. So one is with the lower index and the other one is with the upper index. And we have phi star, right, from this thing. And we have minus phi star partial mu phi, right? And so I have shifted these index in such a way by using the metric that we have, right? By using eta mu nu, right? Okay, so if you look at this, and if you remember the box operator, which was defined as partial mu, then I can write this equation simply as negative iota phi box phi star minus phi star box phi, and this is what I have right now. But if you remember the equation of motion that I derived above for the complex scalar field, we know that this box phi is equal to negative m squared phi. We also know that box phi star is equal to negative m squared phi star. So I have to simply substitute these values in this equation, right? In this equation. And what do I get is, let's do it, partial mu j mu is equal to negative iota phi times minus m squared phi star times phi star minus phi star minus m squared phi times phi. And this thing is equal to 0. So we have partial mu j mu is equal to 0. And so therefore, indeed, j mu is called the conserved current. So this is your conserved current. And we just proved it mathematically. But again, you can ask, well, why? Why is it conserved? So if you think about it in terms of the charge Q, so we have total charge Q, which is defined as the integral d3x of j, or let's say j0. And this definition of the total charge, it satisfies the partial time derivative of the charge is equal to d3x partial time derivative of j0. Right? Now this thing is the same as in terms of 4 vectors d3x del dot j. Now because j has to vanish at spatial boundaries, we can say that this thing d3x del dot j is equal to 0. And what does this tell you? This equation just tells you that the total charge is invariant with respect to time. And therefore, what that means is that the total charge is conserved. And so finally now, moving on to the statement of Noether's theorem. So I'll actually go ahead and I'll write it down. So the statement of Noether's theorem is as follows, that if we have a Lagrangian, and it has a continuous symmetry. So this point is very important, that the Lagrangian has to have a continuous symmetry. Then there exists a current that is associated with that symmetry. So with that symmetry, and this current that is associated with this symmetry is conserved, right? And if you remember, we had over here, if we go back up here where we derived it, let me see, where was it? Yeah, this one. So in this one, we had to have equations of motion had to satisfy, or the Euler Lagrange equation had to be satisfied for this to happen. And one of the other important thing over here was that the symmetry had to be continuous. So that was from this thing. And so that's why we say that if the Lagrangian has to have a continuous symmetry, right? And if we have a continuous symmetry in the Lagrangian, then there would exist a current that would be associated with the symmetry that is conserved. And again, the Euler Lagrange equation has to be satisfied, right? The Euler Lagrange equation has to be satisfied for this to work. Now again, note here that we needed to assume that the symmetry was continuous, so that the small variations that were delta L over delta phi, delta L over delta alpha, right? I'm sorry, the delta L over delta phi, these small variations could be taken, right? And that is only possible if the variations are very small. With that simply means that the symmetry is continuous. And so the Noether's theorem is then not applicable to the discrete symmetries. An example for a discrete symmetry would be a symmetry that is under phi transforms to negative phi. And this is for the case of a Lagrangian that is of the form 1 over 2 phi box phi minus m squared phi squared minus lambda phi 4. So if I take this Lagrangian and if I have this transformation, this would be a discrete symmetry, and the Noether's theorem would not work in this case. Now, before I end this video, or this very long video actually, let's list down some of the important points that are for the Noether's theorem. So the first one is that the symmetry must be continuous. So symmetry must be a continuous symmetry, right? Okay. If it's not, then your delta alpha is pointless, right? Okay. The second point is that the current that we have, J mu, it is conserved on shell. What do I mean by on shell is that the equations of motion are satisfied, right? Okay, and finally we have that it works for global symmetries that are parameterized by a number that is alpha, and not only just for the gauge or local gauge symmetries that are parameterized by functions of alpha that are like this defined. Okay, so with this then, before I end the video, I would also like to tell you over here that what are the steps for applying a Noether's theorem to a particular system. So if you are going to apply Noether's theorem, you take these steps, first one of which is that first of all you have to identify the continuous symmetry in the Lagrangian. And for our example, for the complex scalar field, we identified that symmetry under the U1 group for the field. The next step is simply to calculate the change in Lagrangian density. So that was delta L, right? And after that, once we are done, we calculate the change in each of the fields. That was delta phi. Of course, this changes with respect to that parameter alpha. So it's like this. And once we are done with all of these, the final step is just that we work out the conserved current and the conserved charges. And that's exactly what we did when we started after we derived the Noether's theorem. If you go back over here, when we talked about an example, we had this Lagrangian. We identified what the symmetries would be, which were under phi transforms to this thing and phi star transforms to this thing. Then we calculated the change in the fields over here, which is this thing, right? So the change in the fields were calculated, and after we were done, we computed what is the conserved current, and we went further to write down the conserved charge as well, right? Okay, so this I was not hoping that this video would get this long, but here we have talked about the Euler Lagrange equations. We derived these equations, and we talked about what is known as the Noether's theorem, which is very important in the symmetries that we have in classical field theory. So if you have watched this video completely, by the end of this video now you should be able to write down the equations of motion for a given Lagrangian, and then you should be able to apply what is the Noether's theorem to a system, and which is again you should be able to identify the continuous symmetries in the Lagrangian. You should be able to calculate the change in Lagrangian densities. You should be able to calculate the change in each of these fields. And with all of this, then you should be able to work out the conserved currents and charges.